Well, let's get started. I hate to break up all the conversation, but so any questions? Simon's too far away to ask questions, right? Interface for what? I gave you the methods that the turtle has to implement, right? The assignment gives you the methods. We're going to skip that part. Right. Because drawing on the screen requires a bit more work. And it's not really related to the pattern we're trying to implement. And then the way Java people have to write the screen is completely different than the way Python people have to write the screen, which is different than the Swift people. Sure, yeah. And then when you start at 0, 0 and you say move 10 units, you should go 10 units, right? And so the current location should, instead of being 0, 0, if the angle is 0, then it should be 10, 0, right? And then if you rotate 90 degrees, then we can figure out where it should be. Okay? So the question is, can you use the linked list or a stack or array list? Yeah, fine, no problem. So we want to start with the interpreter pattern, which will help explain what an abstract syntax tree is. So one of the problems we have is that, well, I don't know if you ever noticed that often when you learn something, it's like you go your whole life and you know nothing about this thing, and then you don't see it at all, and then when you learn it, it's like, oh, I see it there, and I see it there, and I see it there. So the same thing happens with, if you've never taken a compiler course, you're like, well, why would I ever need a compiler course? I'm not going to write a new language, right? I mean, whoever does that, I mean, only, weird guys, and they do it once in a while, right? But the problem is, there are a lot of techniques, right, that you learn in a compiler course that you'll use over and over again. Also, you'll find that when you got a file format, it's like, oh, now I got to read the file format. So I got to parse this format, right? Oh, that's like a little language you're writing. Oh, all those tools you learn, right, in the compiler course, like, oh, yeah, this is what I'm going to do now, right? And so if you ever take a compiler course, you realize, oh, I'm using this stuff. This stuff appears everywhere. But if you don't take the compiler course, you're like, well, why don't I do that? I'm not going to write Java, right? I'm not going to write Python 4, so why do it? So the interpreter pattern basically says, yeah, there are times when you have a small little language you're going to use. And it could vary. For example, let's say you're building software for a company so that managers can do SQL queries, right? And so you want to build a little language, little system for them to put together a query and execute it without having no SQL. You basically build a little language, right? And then you want to be able to allow them to put together a program, and then your program has to execute their program, right? And so this is where the interpreter pattern comes in, right? Right? Give them a language, give them the grammar to describe a language. We want to build a system that can actually interpret that, statements in that language, right? In other words, programs. And so again, the basic idea is pretty simple. You're probably familiar with BNF diagrams or these rules. Say this rule, right? Is this, this, or this? So let's look at an example first. What's a Boolean expression, right? A Boolean expression, it could be a variable or a constant, an or an and, a not, and another Boolean expression, right? And then an and is just a Boolean expression and a Boolean expression, right? And an or is just a Boolean expression or another Boolean expression. And the not is just not in a Boolean expression, right? And the constant is basically true or false. And if we're doing Boolean expression, that's all we got. And then a variable could be some sort of string, and the string could then have some representation or some value, right? So these are just the rules, right? And so now, given a Boolean expression, we want to then represent that in such a way we can actually execute it, right? And so, here is a Boolean expression based on that little grammar. And what we want to do is represent it as a tree structure. And so what do we do? Well, how do we apply those rules to show that that particular expression is truly a Boolean expression, right? Well, there's our top level OR, right? And so we have a top level OR node. And the OR has two sub-expressions, right? So in our tree, we're going to have, we've got two sub-expressions. And the one on the left is an OR, and the one on the right is an AND. And so then I have an OR node, and the OR node again has two sub-expressions, but this time one is a constant and one is a variable x, right? And then we do the same thing with the AND. So the basic thing we do is we sit down and we write down the rules, right? And each rule becomes a node, and each sub-rule becomes a sub-node of that rule, right? Of that node. And then I can take an expression like this and build a tree like this, right? And now once I've got the tree, now I can start evaluating the tree, right? How do I evaluate the tree? Well, I start at the root and I say, okay, I want to evaluate the OR, but to do that I need to know the values of the two sub-expressions, right? And so what's the value of this OR? Well, again, I need the value of its sub-expressions. This one's true. Oh, in this case, x is going to be true. And so true or true is true. So this evaluates to true. And so now once I know that, the top node knows that, right? The one sub-expression is true, but now we need to know the value of the other expression. And come down here, it's an and we go WW, and W is false, so false and false is false. And so now the top node knows, oh, true or false was true, right? Not really, because we know that the first one is that if it's an or, right? Yeah. But in general, right, and basically now once they convert this to code, right, we can build this tree, and we can ask the top level, what's your value? And you say, oh, I don't know. Give me the left value, give me the right value, or it's easy, right? Um, Not really complicated, right? Abstract syntax tree. Well, in this case, right, we want to write a code that does this, right? So take that expression, we want to then build a OR class and an AND class. And actually, right, we need a Boolean, we need an AND class, OR class, a NOT class, a constant, and constant variables are basically leafs, right? And so, we're going to build a class for each one, and an AND class knows how to evaluate itself. Like, okay, I need two sub-expressions and get their values, and we got how an AND works, right? It's like, okay, it's only true if both of them are true. We're done, right? And there'll be a OR class and a NOT class, and then when you have an expression like this, we can convert it to a tree like this, and then we can just say, give me, evaluate yourself and tell me what the answer is. Now, once we have variables, then the same expression can evaluate the different answers depending on what the values of the variables are, right? And so when we evaluate this, there's a context it's evaluated in. So far, so good? Now it's called interpreter because it's not compiled, right? Because the structure is going to be this tree, and when you evaluate it, you haven't taken that expression and converted it to a binary operation at the machine level. It's just like, no, here's a AND node and OR node, and those are classes in Java or Python, right? And then at runtime, we say, give me your result, and then we execute all these operations at high level, which is what Python does, right? Right, it's an interpreted language, and so when you write a program, right, you interpret the program, build that syntax tree, and then you can evaluate that tree, which is one reason why it's slow. And then, okay, we might create a interface here because, and we need a context because we need to pass those values around, right? And then our AND class, just has two operands, right? And evaluate passes the context on and says, give me your result and give me your result and AND together, return it. That's, right? And then the toString is sort of nice, but then you can actually see what's going on because when you're debugging these things, if you get the tree wrong, it's going to get the wrong result, and you're going to be like, why, what's going on? And no, human conflict is sort of silly. I mean, of course, as a variable, then, well, you don't know your actual value, right? You have to figure out from the, you have to have the context. Well, give me my current value, and then grab all the context and then return that value. Yeah, yeah. I mean, in the Boolean expression, unless we're dealing with multivariate logic, but we're not. In this case, the context was, I just store things in a hash table, makes life easy. Um, and then to do the expression, right, we have to sort of build up that tree. So now we can come back and explain this, right? So each of our grammar rules we turn into a node, and each sub rule becomes a sub node, right? And then this node has to know how to evaluate itself given the results of those sub nodes. And then we can explain this, right? Um, given the grammar and given a statement in that language, we want to then build that tree for that expression. And then we can actually evaluate that expression given the context if there are variables in it. And typically, yeah, you need some sort of interface for all the nodes to adhere to, because any given expression, you don't know, it's going to have sub-expressions, right? So we don't know which ones they are, so we need that interface so that we can talk to it and hold it, right? And terminal expressions don't have sub-expressions, and so they're true or false variables, things like that. Piece of cake, right? Famous last words, right? But the idea is pretty straightforward, right? Right? Like right here. There's a rule, and there's a rule, right? And it's Boolean expression and Boolean expression. Well, the root node here, this is just, here's my rule, right? It has sub-expressions. And so in this case, that's my R, and this is R1, and that's basically R2, right? Now notice, let's actually do it here, because it'll make more sense to you. We haven't talked about how I read this in and produce that, right? Here I've hard-coded that program to represent that expression. You're pretty much guaranteed that's never what you want to do, right? What you really want to do is write a program that reads this in and then produces that tree. And to do that, you have to parse that expression, right? Now, the interpreter pattern doesn't talk about parsing. It's how to represent the language and execute it. Which is one reason why I've always fully parenthesized it, because that does make life a little easier in parsing it, right? So there's two complications for your assignment that I skipped over here. One is how to parse those expressions, right? That's one reason why the repeat statement has an end at the end, to make that a little easier to deal with. The other one is I've just shown a single expression, right? Where the program has multiple expressions. Well, that's because you have to define a rule for a program, and a program can have multiple statements, right? And then you have to define what a statement can be, right? And the different versions of statement, and then which statement can be, right? I just told you the answer to one of those complications. And the other one, you'll figure it out. Right, so some consequences, it's easy to extend the grammar to change it. Why? Well, because adding to the grammar means adding a new rule. Adding a new rule basically means creating a new class that represents that rule, right? And the process of taking the rule into a class is fairly straightforward, and right, it's each rule represents a class that has a subclass or interface, and then it has to hold each one of those sub things, and then you have to understand what that rule does to actually evaluate it. In our case, ands or ors, right? So implementing the grammar is pretty easy, right? Yeah. If the grammar gets really, really complicated, it's going to be hard because you have lots of classes, right? And the Java syntax is actually quite involved, right? You're probably not going to want to use interpreter pattern to implement Java. There's too much there. And so there's a bunch of compilers that you use. You feed in the grammar, and then it spits out the code to represent that grammar. Well, but these days, what you really want to do is you want to take your grammar and translate it to the LLVM grammar, and then use it to generate your binary code for you, because it's way more efficient than you're going to be doing it by hand, which is why most new languages use it now. New ways to interpret expressions. That's one of the things you'll be doing in your assignment is once you've got that tree, when we talk about the visitor, you can see we can send a visitor to it and evaluate it differently for different visitors. Right. So in your assignment, you're going to create 2 different visitors. One is going to go through and return a list of all the mementos, right, in order. So then we can then sort of run that program backwards and forwards, right, by just taking the mementos and changing the state of the turtle. The other one is, well, just computing how far the turtle goes. And the reason we have to do 2 of them is to make sure you don't mess up the visitor pattern. If you do it once, then you try and optimize it, and then it doesn't become a visitor pattern anymore. Right? So it's for each rule in the grammar.
For each rule. So it's you to have like I don't know if this is what the how like define how each set based off.
Yeah, I mean, basically, the compilers, you give it here's the grammar, and then it then produces the code to actually build the tree for you. Yeah, it doesn't talk about the pattern doesn't talk about how you actually parse your sentence or your program to convert it into the tree to interpret it. We haven't talked about the flyweight, but if you got a lot of the terminals I use a lot, then we can use the flyweight to not have hundreds of them, just have one of each and then reuse them. We'll see that when we talk about the flyweight pattern. Yeah, an iterator can use it to traverse it. And we'll be looking at the visitor, how to use that on it. Any questions about the interpreter pattern? Do we use serializable? No. To parse it, I mean, you read the text and you're like, okay, where's the next token, next token, next token? So you're asking, do we do a 1 pass or a 2 pass on the reading the program? 1 pass is fine. Say that again? Right. The question is, will the first statement be used relative to the second? That depends on the statement, right? If the statement is turtle rotate 90 degrees, that changes the state of the turtle, but we don't, that state change is used, but we don't use actual statement, right? If you've got a variable and you assign a variable of value, then yeah, that's used later whenever you use that variable. Any other questions? Okay, then. The visitor patterns. So the intent is to represent an operation, right, performed on elements of a structure. So when we think about it, right, when I showed you that tree for the expression, right, it's easy to see how you would then, okay, my AND expression would now have an evaluate method, and like I showed you, it would just be give me the, compute the value of the subexpression, compute the value of the other subexpression, and then AND them together, right? So we build that the operation for that structure inside each node, right? So we just say, go to the top level and say evaluate, and it all does it, right? And most of the time, that's what you want to do, right? Because it's straightforward, and then each part of the structure knows exactly what it's supposed to do, and it just does it. But there are times when that doesn't quite work. What happens if we want to do not just one operation, but two or three different types of operations on the same structure, right? Every time we want a new type of operation, then we have to modify all those classes, right? And add that another operation, evaluate 1, evaluate 2, evaluate 3. What's the difference between evaluate 1 and 2? I forget. I mean, what is it? And if there's lots of classes involved, it's going to be a pain, right? And that's where the visitor pattern comes in. So we're going to, instead of the operations being in the structure, right, they'll be in the visitor. And so then we're going to take this visitor object, and then it's going to go and it's going to visit every element of the structure. That's sort of easy to understand. The problem is that the visitor pattern, when I create a visitor, say, to compute the distance, right? Now my visitor is just going to compute the distance. But it may be, every different type of node it goes to, it may do something different, right? So we need to know what type of visitor it is. Oh, it's a distance visitor. And we need to know the type of node it's visiting, right? So at runtime, there are two things that are going to determine what operation we actually do in the visitor. Does that sound familiar?
Sounds similar to the strategy. Like you're defining outside of the class and you're passing functionality into.
Right, so we are doing that. But the strategy pattern just does the same thing, right? Where here is we're going to pass this visitor, the same object around the different elements of the structure, and depending on what type the structure element of the structure it is, it'll perform differently. Yeah, oh. And so now at runtime, there are two things which determine what we're going to do. And that's double dispatch, right? But Java and Python and Swift don't implement double dispatch. And so how do we implement double dispatch in languages that don't have double dispatch? Oh, the answer is you do single dispatch twice, right? And this is where the visitor pattern looks weird, because we're going to, when I want to do the operation, you're going to call two methods, because each method gets to determine, oh, I'm now on this type of visitor, and now I'm on this type of visitor on this type of node. And so, simple example, I got sort of a tree thing, and I have internal nodes and external nodes, and I want to do different types of operations depending on what's internal or external. And okay, I may want to, just print a tree out, but how do I want to print it out? Where do I want to print it, right? So if I do print out HTML, it's different than doing a PDF print, right? Because HTML is like, oh, that's going to be really tricky. You have to draw those lines. PDF is like, does anyone know how to write PDF? No, it's really complicated, and it's completely different than HTML. And using tech, okay, I mean, you can do in tech, but again, that's going to be a completely different operation than doing it in PDF or HTML, right? So I think they're completely different. And they're like, well, do I want to build each one of those into the tree, or is it better to create a visitor to do the PDF, knows how to do PDF things, another visitor knows how to do, right, tech, another one, HTML.
Visitor has like or do something.
We will build a visitor to do, say, tech, but it will do different things based on whether it's an internal node or external node, right? So for each type of node or element we got in our structure, there'll be a separate method in the visitor class to do that.
It's just this, do this, do this.
No, these methods are not.
Okay.
They're not if else do that. No, we want to avoid that. Yeah, right. If it's double dispatch, then we could just have single method, and we have one for internal node and PDF and internal node HTML, right? But we don't, so we're going to have, and the way we get to them is going to be send over there and send over here, right? Because we need two single dispatches to equal a double dispatch.
Or each for each.
Well, we'll see. Yeah. So let's assume, right, we've got different types of documents. And so this is what we want to avoid, right? Is, if it's an inner node and the output is HTML, then do this. If it's a leaf node, do this, right? Not going to work. I mean, this is just going to be terrible, right? It'll be hard to maintain because, and so we can do this, right? Um, so here we're getting rid of, we're separating out whether it's a leaf node or internal node, right? But then that's going to be better, but then inside our print leaf node, we have to then check what type of, right, what type of thing it is, and again, that's going to be hard. So we don't want to do that. We got these hidden case statements, and every time we want to extend a different, we have to add it, right? And so, yeah, so if we have, a tree printer, and then if we had double dispatch, we could do this, right? But that won't work in Java. Um, and in Java, that's a compiler, but they can't figure out which is right. Um, right. We've talked about this several times already. And so we'll create different printers, right? And then, we're gonna, so our top level class it'll go through all the nodes, right? And then it'll call print leaf node, print inner node. And then the HTML printer is going to have a print internal and a print leaf node, right? Well, and here the issue is, right, we have single dispatch, right? So at runtime, we're going to look at X and see what type of thing it is. So in our nodes, we're going to add methods. And so what the inner node is going to do is we're going to pass in a tree printer, and then we're going to call the print inner node on that printer, right? So we pass in the visitor to the node and say print on it. And then what that print method does is it calls the print inner node on the visitor. Right. This is how we're getting double dispatch, right? Because I call the print node on the node, and then at runtime we figure out what type of node it is, and then that node is going to call either print inner node or print leaf node on the visitor. Right? And this is the weirdness I talk about because you pass in the visitor to the node and right say visit this, and then that node says okay, now you go do that, right? It's roundabout, right? Sort of. When I say node, we're talking about instances of the class in that structure. And this is a part that students often want to skip. Like, well, why am I doing it twice? All this check is type and then call it directly. It's like, no, we don't want to do that. And then they try and find tricky ways around it by, having methods called the same thing, and you have to be careful because you have to keep track of what is done at compile time and what's done at runtime. Does it make sense? Yeah. Right now we use polymorphism. Or how? When I let's see, do I actually do it? No, I don't. Oh, pass the wrong button somehow. No, like this. So now what I do is I create the printer I want, and then I can call print tree on it and give it the tree structure, and then it iterates through all the nodes, right, and passes the printer to each node, and each node in the tree then calls print inner node or print leaf node, and then it does the right. Then we got the right code without any case statements. If you want to add a new type of visitor, we don't have to modify the structure, right? We just basically create a new subclass of our abstract visitor class and implement the methods on, you know, print inner node, print outer node, or leaf node, and we're done. If we add new types of nodes, right, in our structure, then we have to go back to all our visitors and add that visit or print that type of node to each one of them.
Visitor functionality, but it's all these terms you're passing class.
Right.
So that's not taking like, I mean, it's just taking the base class.
Well, but when we call this inner node, right, we're determining at runtime the actual class of that printer. So we are actually specifying which operation based upon the type of the node we're visiting and the type of the visitor. Right. So yeah, we can add more types of visitors. The other thing is what people don't talk much about when you're doing object-oriented programming. One of the things you do is you divide things into pieces, right? So how does a binary search tree work if you build different classes for the tree? Um, Operations for different type of node are in the nodes, right? Whereas usually you used to have them in one place, right? So the visitor is going to take all the related operations of that type and put it into the visitor class. So they're in one place again. Um,
This would still have the grammar.
um, well, the question is, I have a structure, some sort, right? In our case, it's a grammar. Um, so if you add a new rule, then the visitor has to be modified to take care of that, be able to handle that rule, right? So the visitor pattern makes it easy to add more visitors, but to extend the structure, in this case a grammar, then you have to modify each visitor. Yeah. Yeah, I won't go into this. It is possible to just, instead of say print inner node, print outer node, we can just do print node. We get by with that, but we still need to know what type of node it is, otherwise right, so we still have to specify that. Um, yeah, I mean, again, that's, if you want more types of nodes, we need to modify things. Um, so the visitor pattern doesn't use, print this or print that. You're going to see except, um, and the reason is you may be doing other things like printing, right? Um, so it's more generic. It's like, okay, we're going to visit you, and then the visitor may print things out or may compute distance or whatever, but we don't know what type of thing it's going to be. So it's just usually accept, right? And so each node has an accept method, and then the visitor has a visit this type of node, visit that type of node, and then we call it. And there's our visitor, right? So the interface in this case, visit binary tree node, visit binary leaf node, and then the HTML printer implements those two methods, and then it does what it has to do to print in HTML, which I'm sure would be complicated in HTML to print out a binary search tree.
So like in that example, so like in that case, that binary that
Um, yeah, in Java, most of the time, an abstract class and interface are interchangeable. Not quite all the time. And there's some things you can do in an abstract class you can't do in an interface. In abstract class, you can actually have methods which are implemented, where the interface you can't. Unless, of course, you're using Java 11, and then things are more complicated. But not many people are using Java 11 since it came out yesterday. And if you're using Java 11, you have to be careful because they changed the license on you. If you download it directly from Oracle, it's no longer free for commercial use. But there is a open SDK version, which is licensed is free. So download it from there instead of Oracle, unless you want to pay for support. And then, so here, yeah, when I create this visitor, um, and I can use an iterator to go through them all, right? Um, in my tree, and then I can go through all the nodes and just call accept on them, because now what's going to happen is at runtime we'll look at the actual class of what current is and call the right accept. And then once you're inside that accept, right, we're going to call, visit inner node, visit outer node, whatever the right thing is. And then here's the whole tree example. And basically the idea is, right, is we have this visitor and we're going to pass it, call accept on the top node, right? And then it's going to say visit me. And then it'll say go visit this guy and go visit this guy, right? Anytime you say visit, right, there's an accept, and then we say, call this visit node on the visitor.
For having at least in the case of like even printing.
I mean, the visitor can build up information as it goes along and do, I think, at the end, right? It depends on what it's doing, right? Yeah, and this whole thing, right? We call, accept on the leaf, and the leaf says visit me, right? So we're using single dispatch twice to get the effect of double dispatch. And so implementation issues, um, who determines the order in which you visit the elements in the structure? And there's basically three answers, right? One is the visitor can do it. Um, the element in the structures can do it, right? In a binary tree, it's really easy to say go left, go right, right? Or you can have an iterator. And depending upon what the situation is, one may be better than the other. Right? So I talk about when you want to use this. Um, one thing to be aware of on the assignments, I'm trying to pack in as many patterns as I can to get experience, but I try not to make the assignments too big. So usually the patterns density is probably higher than it should be in normal code, but the whole point of the assignment is, some of you are still slightly fuzzy on the visitor pattern, and it'll become much clearer when you actually do it. And then 2 days after you turn the assignment in, it'll be like, oh yeah, now I finally understand it, right? Right, yeah. But until you actually go through the pain of trying to make it work, right, then you don't quite understand some of the details and subtleties and some of the problems. Yeah, so it makes it easier to add new operations, right? You just accept all the classes in the structure, and then, right, we can now just create a new visitor for each operation. Um, it takes all the operations of that particular type and combines them into one class, which is sort of nice. Because now, but yeah, adding more elements to your different types of elements to your structure becomes hard because you have to find all your old visitors and change them and change the interface. Um, you can accumulate state as you go, right? As you go through, you can accumulate state, and then and that's one of your visitors you'll do is go through your that syntax tree for different statements. Say, well, if it's a move statement, I have to figure out how far I've moved, right, and keep track of the distance. Break encapsulation is because the fundamental idea is you want to keep operations and data together, right? And So now what we're doing is the data is going to be in your structure and the operations are going to be in your visitor. um, yeah, so what happens if, right, the classes you want to visit, you don't have a source code for, right? There's someone else's classes. How do you then do a visitor pattern on that? Well, in most situations it's sort of hard. Um, Many years ago, there was this popular idea called aspect-oriented programming, um, where the idea was that you find that certain things span different classes. We want to do certain operations across multiple classes. How can we do that without having to add code to each class? For example, logging, right? Um, you have a system that maybe you have 50 classes in it, and you want to log to what's going on at various points for security reasons or debugging reasons. Do you really want to? I mean, right now what you do is you go hand add log statements every place, right? Um, and the aspect-oriented program would say, well, look, any method of this type in any class, um, before you call it, just call this log, right? And so there'll be an aspect which they specify which methods and which classes you would add that to, without having to go and actually edit each of those classes. And so if you're doing aspect-oriented programming, we could add this accept method right to each class. Of course, now, with Swift, you've got extensions. Even if you don't have the source code, we can add accept method to it. In Python 2, you used to be able to do that, but not in Python 3. So but aspect-oriented programming never really caught on. It was a little bit too complicated, and people couldn't figure out. So an example of using visitor pattern. So there's this web framework called Magritte. It's named after this famous French artist who liked to draw these weird things. And so the problem is when you've got, for example, we get a form, right? And on the web, there's some things you have to do. You have to display the data, and so they can actually see the form, the labels. You have to enter the data and collect it. We want to validate the data, make sure that this field is supposed to be an integer, and they type in string, and then okay, we need to check that before we try and do something with it, and then we got to store the data, right? And so they wanted to use a visitor pattern to do this. And so what you do is you specify the structure that you want, right? So they created a domain model class to represent the description of what it's going to be, right? So description of what the form is going to be, well, you need to know what the fields are, the data types of the fields, any constraints for if the string is an integer between 1 and 50, that sort of thing. And once you've got that description, right, we can now, description for each field in the form, right? We can then put that description together and build a structure. And now we can create a visitor to do, one visitor to actually create the display for it. So it'll convert the HTML and so people can see it. We can do another one, right, which when you get the data, it'll validate the data for you. And so you create this model of what you want to do, and then there are visitors already made for you that will do these operations. Generate the HTML, generate the form, validate the M4 data, and actually save it to the database. So basically, literally you would create a person object, and you'd have a description of what all the fields are supposed to be in there, and then it would generate a page like this automatically. And it would validate the data for you. When you hit save, it would store in a database for you. And again, because we had that structure, and then we could pre-build the visitors to actually do each operation. Well, no, CSS can't validate your input. CSS only describes the layout. Well, this is all done in a particular language, and it would generate the back end and the front end for you. So you create a person class, and you give a description of all the fields in there, and then you could basically, that code would generate the HTML page for you. And when you hit submit, or save, it would check to make sure that it would generate the JavaScript to check that if the input was valid or not. It's just the basic idea, right? Is we can actually use this in various places you may not think about to actually do something useful. Yeah, and there's, like I said, there's this book that talks about refactoring to patterns. A visitor is a good place to accumulate results, right? So you go through and calculate all these things, and when you're done, here's the answer.
With the pattern and those go
Um, it doesn't have to be a tree. It's basically it could be any sort of structure. It could be a graph. It's the easiest one to talk about and visualize, right? That's the one we're most familiar with, but no. And then, of course, right, once we have language which would double dispatch, we don't need the visitor pattern. We just have, one method, and each method will have the two arguments, right, of different types. And we saw this before with Lisp and with Julia. But again, the main point here is just that, in your career, other languages come out, right? And they'll have different functionality, and some of that functionality may remove the need for some of these patterns. Yeah, I think it's harder to implement. And the question is, the trade-off between the difficulty of doing it and how important you think it is. And you have to keep in mind, um, Java comes out of the mid 1990s, so it's mainly developed in the early 90s, and compiler technology has changed quite a bit since then. One of the things that's hard for us to, to recognize is that when you look at mathematics, I mean, it took centuries for them to hone their notation, right? In some cases, not centuries, but a millennia. Um, we're only 60, 70 years into the computing world, and to expect that we've fine-tuned all these languages is just nonsense, right? Um, we think we like to have all these language wars. My language is better than your language, and it's like, oh yeah, come back in 50 years, and you're like, you realize that all the languages we're using now are not very good, right? And we come back in 200 years, I mean, then we might have a good language. So now you know the interpreter pattern, and now you know the visitor pattern. What's that? No, you'll be experts after you finish the assignment.